Right, so diving into semiconductors, which like I said is the first completely new topic that we're discussing in this course. And so in this chapter, we're going to learn about the basic properties of semiconductors, in particular silicon, the material that's used to make most modern electronics. We're going to talk about doping, okay, and what that means in the sense of dealing with semiconductors, how that changes the conductivity of a pure silicon crystal. We're going to talk about the different mechanisms by which current flows inside of a semiconductor, drift and diffusion current, which are carried by drift and diffusion charge carriers. We're going to talk about the structure and operation of a p-n junction. That's really the example that we use as the basis for discussing semiconductors. And that makes sense because it is the simplest and most basic semiconductor device. Does anybody know what the other name for the p-n junction is? It's a component that you've definitely used before in lab. Exactly. Diode, yes. So the diode is a component that allows current to flow only in one direction. p-n junction is just a way of describing the diode that's based on the structure. It has a p-type dope semiconductor that intersects with an n-type dope semiconductor. All right, so beginning here, what is a semiconductor? As the name would suggest, it's a material whose conductivity is between that of conductors like copper and insulators like glass or wood. A single element semiconductor would be one that's only silicon, only germanium. There's also compound type semiconductors such as gallium arsenide and a million different other ones. But we're going to be focusing on silicon. Now, this chapter is a little bit different from chapter 2. The first way in which it's different is we do touch upon a lot of stuff from chemistry and physics that you may not have talked about in a while. And the other way that it's different is the kind of questions that one could ask about this chapter. There's a lot more new theory, vocabulary words, I guess is the right term to use. So the way that we test this chapter is a little bit different. So you do need to spend some time, perhaps, looking over the terms and making sure you're up to speed on those. All right. So valence electron. What's a valence electron? Can anybody tell me? Yes.
Like the outer ring electrons that can participate in bonding.
Exactly, right. So you have an atom that's composed of a nucleus, and it's surrounded by electrons that orbit it. The orbits of those electrons take the shape of different shells, which are called S, D, F, whatever the names are. And a given shell has a number of electrons that's required to fill it. Every atom, its goal in life is to fill its outermost shell. That's when it's most stable. And so a valence electron is an electron in the outermost shell that is unfilled. Okay? And so those electrons are going to be available to participate in chemical bonds. Atoms with one or two valence electrons more than a closed shell or fewer than a closed shell are highly reactive because the extra electrons are easily removed to form positive ions, and then on the other side of the coin, right, easily form negative ions. A covalent bond is a form of chemical bond in which two atoms share electrons. So let's say we have atom A, it's missing one electron from its outermost shell. Atom B, same thing. They can form a covalent bond, share that pair of electrons, and both will have filled their outermost shell, forming a more stable balance of attractive and repulsive forces, therefore fulfilling the atom's goal in life. All right, so when we talk about silicon specifically, silicon has 4 valence electrons in its outermost shell of 8, so it requires 4 more to complete it. And each pair of, the picture does the best job of describing this. The silicon forms a lattice structure which looks like this, where each atom shares one electron with its neighbors. and you end up with this lattice structure. Covalent bond, covalent bond, covalent bond, covalent bond, full outermost shell. Now, silicon at low temperatures is not very conductive, right? At absolute zero, it would theoretically not conduct any electricity. And that's because at low temperatures, all of those covalent bonds will remain intact and no electrons will be available for conduction. What happens when you increase temperature a little bit and get to room temperature? When you get to room temperature, there will be some thermal energy inside the lattice, which means that, we can imagine it like shaking slightly. And so that will cause some of the covalent bonds to break periodically. And when a covalent bond breaks, what we'll have is electrons will be freed. They'll wander from their parent atom, or what was their parent atom, and be available to participate in conduction. Whenever an electron is freed, it also creates a hole, which is a spot in a covalent bond where an electron can fill. So for silicon at room temperature, the conductivity is going to be greater than 0. So the process, like it says at the top in the yellow box, the process of freeing electrons, creating holes, and filling them is what facilitates current flow, right? That movement allows current to flow through the semiconductor. So here you can see an example. Thermal energy causes this one electron to be freed. It goes away, which leaves a hole. Another electron comes to fill that hole. And so this process facilitates current flow, right? The electrons can keep moving from one end to the other. Practically, it wouldn't be the same spot always that's having the electron freed from, right? It would be here, then down here, then somewhere else. It should be random. So, intrinsic semiconductor. An intrinsic semiconductor is one that's not doped. We haven't talked about doping yet, but I can tell you now, an intrinsic semiconductor is one that's pure. So it only has silicon atoms inside of it, ideally. Generation is the process of freeing electrons and then creating holes. So far, the only mechanism we've talked about for that is thermal energy, temperature. The generation rate is the speed with which this occurs. And then we have recombination, which is the opposite. So when an electron finds a hole, they recombine, which then stabilizes the covalent bond and essentially kills the free electron and the hole. Recombination rate is the speed at which that occurs. Generation rate is the speed at which generation occurs. So generation may be affected by thermal energy. For an intrinsic semiconductor, the generation and recombination rates are equal to one another, and they'll be a function of temperature. So at absolute zero, the generation rate would be 0, no conductivity. At room temperature, it'll be larger. If you were to heat it up to an even hotter temperature, the generation and recombination rates would increase. So one kind of generation here is thermal generation. So when the free electrons and the holes are generated by temperature, we have equal concentrations of free electrons and holes. The electrons will move randomly throughout the material and then sort of recombine somewhere else. Don't laugh at the note on the next slide. I guess I was testing the pen, so I wrote test using the pen at the top. I'm going to delete that. So in thermal equilibrium, the behavior below applies. So this is an important, yes?
Could you just restate what thermal generation was?
Thermal generation is simply just the generation of free electrons and holes that's resulting from heat, from the thermal energy that's in the lattice structure. All right, so this equation here is an important one. We're going to use it a lot, actually, even when we talked about doped semiconductors. And what it says is that in thermal equilibrium, the number, or we could also say the concentration of free electrons, which is equal to the concentration of holes, that is equal to, and I actually have the rest of the values on the next slide labeled. So we have a constant, which is 7.3 times 10 to the 15, with these units for silicon. Temperature in Kelvin. Eg is the band gap energy constant, which is 1.12 electron volts for silicon. And K is the Boltzmann constant, which is also shown. So, for our intrinsic semiconductor, the concentration of free electrons, which is equal to the concentration of available holes, is defined as a function of all of these. The only one that really changes is temperature. So you see that as you increase temperature, the concentration of the free electrons and available holes will also increase. So why can we not use thermal generation to affect meaningful current conduction? So first things first, the silicon crystal structure we described previously is not really that conductive at room temperature. Even at room temperature, you're not going to be building any iPhones from that, okay? Additionally, the dependence on temperature is not desirable. We don't want dependence on temperature. A lot of the work that we do in device design is to reduce effective temperature. Right, we want something to work the same at room temperature as it does in that range. We don't want the iPhone to work differently when it's cold outside. So that's, besides the fact that it doesn't provide us significant current conduction, it's not really the independent variable that we're looking for. We're not looking to control things with temperature. Yes?
So, you know how you were saying before with more current, like the electrons or whatever this will heat up? Does that heat from the current, like moving through the holes, affect it also?
It does, but that's small. It's really a small amount of current that we're talking about at this point. So yeah, I mean it would, but this is like nanoamps or smaller that we're talking about. So it would, but not really. Not really in this case. You would have to heat up for the semiconductor to conduct that much current thermally. You would have to heat the thing up so much that, again, the heat generated by the current would be negligible. You put it in an oven and warm it up to, 5,000 degrees, then it doesn't really matter, the other component. Okay, so how can we fix this problem? We want to control the conductivity. We want to increase the conductivity, but we don't want to do that via temperature, and so what we're going to use is doping. So doping is the intentional introduction of impurities into the intrinsic semiconductor for the purpose of changing its carrier concentration. So there's two types of doped semiconductor: P-type and N-type. P-type, positive type; N-type, negative type. So for P-type semiconductor, the silicon is doped with an element having a valence of 3. Remember, our silicon has a valence of 4, so when we use 3, that'll automatically introduce positive ions into the lattice structure. For the N-type, we're going to dope it with an element having a valence of 5, which is automatically going to introduce spots where we have one more electron than is required by the lattice structure. To increase the concentration, for the P-type semiconductor, the goal is to increase the concentration of holes. And then in N-type, we're increasing the concentration of free electrons. Both have the same effect. When we have more available holes, it provides spots for electrons to travel through the lattice. When we have more free electrons, it makes electrons available for conduction. Again, both of these have a similar effect on conductivity. One example we can use for the P-type semiconductor as an impurity is boron, and then one type we can use for the impurity in the N-type is phosphorus, because they have the appropriate number of electrons in their outermost shells. All right, so what do the lattice structures look like here is an example of p-type. Here's an example of n-type. What we do is we replace the innermost, well, it doesn't have to be this one. We're focused on this atom. But we replaced one of the atoms with a boron atom. And so what we end up with is a missing electron somewhere in the lattice structure. Now, it really doesn't have to be associated with the atom because everything is fluid here. But you can see that somewhere in the lattice structure there is a hole that is created by essentially robbing it of one of the valence electrons. All right. Now, for the n-type semiconductor, what we do is we provide it an atom with a +5 valence number, and then the result is there will be a free electron donated by the impurity that's going to be floating around and is going to facilitate current conduction. So these pictures demonstrate how the impurity affects the covalent bonds and then generates an available hole or a free electron. Okay, so now let's talk about the effect of the doping. So, first things first, we're going to assume whenever we dope that the concentration of the doping impurity is much greater than Ni. If you remember, so Ni was the concentration of holes as well as the concentration of electrons that are thermally generated for the intrinsic semiconductor. That number is relatively small. If we're going to bother doping, we are going to dope it with a value that's going to be multiple orders of magnitude greater. And so we're going to assume that as such. We're not even going to talk about the case where one would dope it at such low concentrations. So Na is going to be much greater than Ni, where Na is the concentration of the acceptor atom. Why do we call it the acceptor atom? We're talking about a p-type doped semiconductor. The impurity that we inject will have a valence that will be short one electron, which means it'll have a hole, which means it's accepting electrons. Okay? So therefore, this equation applies. The number of holes, P, in the p-type semiconductor, subscript P, is approximately equal to the number of acceptor atoms. Why is it approximately equal to? Because to make it exactly, you would have to do plus n sub I, the number or the amount that's thermally generated. But again, because we're assuming that the concentration of acceptor atoms is so much higher than Ni, that part doesn't really matter. It's so small. And so we should talk about, well, actually I'll talk about that in a second. For the n-type doped semiconductor, we have a similar situation. And so again, we're assuming that the concentration of the donor doping agent is significantly higher than what would be present intrinsically. Donor for an impurity that donates an additional free electron to the lattice structure because it has a valence of 5 as opposed to a valence of 4. So, the concentration of free electrons, N, in an N-type doped semiconductor, subscript N, is approximately equal to the concentration or the number of the donor atoms. We call these the majority charge carriers. Okay? We'll talk about the other side of that coin in a second. So in a p-type doped semiconductor, the majority charge carrier is an available hole. In an n-type doped semiconductor, the majority charge carrier is a free electron. So N sub N, concentration of free electrons in an n-type doped semiconductor. P sub P, concentration of available holes in a p-type doped semiconductor. Again, the key, not to be repetitive, is that the number or the concentration of free electrons, which is proportional to conductivity, is dependent on the doping concentration and not on the temperature. So we can control that whenever we run the chemical process and create our semiconductor. Right, that's when we would set that value. Okay, so we said that there were majority charge carriers. There are also going to be minority charge carriers. So when you have a p-type doped semiconductor, you're going to have a lot of available holes. But that doesn't mean that there's no free electrons. There are going to be some that are a result of thermal generation. So how do we calculate that number? We use this equation right here. The number of majority charge carriers times the number of minority charge carriers is equal to Ni squared. So how do we use this equation? Ni, we have an equation for that. Right? It's bt to the 3/2 k times whatever else. The number or the concentration of majority charge carriers is going to be determined by the concentration of the doping agent, so we control that. And then you can calculate the minority charge carrier. So again, looking at the notation here, this is still for the p-type doped semiconductor, so subscript p, but now we're talking about the other charge carrier, the minority charge carrier, which is free electrons, so n sub p. Same equation applies for the n-type doped semiconductor. The majority charge carrier times the minority charge carrier concentration equals Ni squared. So 99% of the time, you're going to be using the equation in this form. You're going to be able to calculate Ni from the constants and the temperature. You're going to be given the donor or the acceptor atom concentrations, which are the same as the majority charge carrier concentrations. And then you're going to use that to figure out what the minority charge carrier concentration is. A lot of this stuff begins to make more sense once we start doing examples and you get into the groove of dealing with it. Okay, so a little summary for both the p-type and the n-type semiconductor. The good thing is that you really are not learning two separate things, right? They both are, the parallels between them are so strong. So if you can understand things in terms of majority and minority charge carriers, donor and acceptor, I mean, it's really the exact same thing. So for both of these, the minority charge carrier will have a dependence on temperature, n sub p and p sub n. So whenever the letters don't match, you know that that's the minority charge carrier. The concentration of the majority charge carriers, actually that's not what that's, oh here. Let's go in order. Okay, so for the p-type doped semiconductor, the concentration of holes will be much greater than electrons. Let me change that. So the concentration of majority charge carriers, P sub P, will be much greater than the free electrons, which is N sub P. Over here, the concentration of free electrons will be much greater than holes. Again, for both of these, concentration of majority charge carriers will be greater than the concentration of minority charge carriers. Holes are the majority charge carriers, free electrons are the majority charge carriers, and then vice versa. Whatever is the majority charge carrier, the opposite is the minority charge carrier. All right. So let's get into our first example. Consider an N-type doped silicon structure for which the dopant concentration is 10 to the 17 atoms per cubic centimeter. Find the electron and the hole concentrations at T equals 300 K. Okay. First things first, these do match, right? We have an N-type doped semiconductor, therefore we will have a donor doping agent concentration. So Just something to check. So how are we going to solve this? Let's walk through it maybe conceptually first, and then we'll do the math. It's not very difficult. It's really like 2 steps. So it's asking us for the electron and the hole concentration. So which one can we get right off the bat? What's the majority charge carrier for this type of? Exactly. So then it should be really easy to figure out what the concentration of the free electrons would be, right? That's going to be equal to? Exactly. So we know that right off the bat. So the concentration of the free electrons is 10 to the 17 electrons per cubic centimeter. The slightly harder part, still not hard, but slightly harder, is figuring out what the minority charge carrier concentration is. For that, we're going to use the equation we saw, Ni squared over the majority charge carrier concentration equals the minority. Okay? In order to use that equation, we have to calculate Ni using the temperature and all that good stuff. So let's take a look at the response. The answer. Okay, so this we already answered. Step 2, define the relationship between Ni and Nd. Again, we know the minority charge carrier concentration is equal to the intrinsic value divided by either Nd or Nn. They're both the same. So before we can use this, we need to figure out what Ni is. Ni is equal to our constant times temperature, e to the negative band gap, divided by 2 Boltzmann constant times T. Now what I did was I went ahead and solved for this. Our value of Ni is 1.5 times 10 to the 10 per cubic centimeter squared. I encourage you to go and do that calculation yourself, again, to check. The only variable, in order to use this equation, the only variable that you need is temperature. Right? Everything else stays the same. The B constant, the Boltzmann constant, the band gap energy, all those are the same. Now, and then lastly, right, we apply this equation, so Ni squared divided by Nd, and that gives us a minority charge carrier concentration of 2.25 times 10 to the 3. So this makes sense in multiple regards. First is, if we're going to bother doping, we're going to dope it several orders of magnitude higher than we would have charge carriers generated thermally. So the number of charge carriers generated thermally is approximately 10 to the 10. We're doping it 7 orders of magnitude higher than that. So that makes sense, given what we've said. The other thing that makes sense is that the magnitude of our minority charge carriers is significantly less. So that's 14 orders of magnitude difference between the majority and the minority charge carrier. Okay, so that is the end of the first piece of this. The next topic we're going to discuss is current. So really the end goal here, where we're moving toward, we want to describe the chemistry and the physics behind the semiconductor appropriately. We want to define the structure of the p-n junction. We want to use those expressions to describe the p-n junction. But we eventually want to get to current. Okay, our goal is to create a VI relationship. What's the relationship between voltage applied and current flowing through the p-n junction? And that will lead us to the diode, and that will lead us to using the p-n junction inside of a circuit. Because this level of resolution, this detailed internal look at a p-n junction is good for learning and instructional purposes, but it's not very useful in terms of a circuit, right? You're never going to be handed a design and be designing it from this low level down here. Which means we want to start talking about how does current flow in a semiconductor. So the first type of current that we're going to talk about is called drift current. So there's 2 different kinds, drift and diffusion current. Drift current is attributed to or is excited by an electric field that's applied. So what happens when an electric field is applied to a semiconductor crystal? Just like any material, holes are accelerated in one direction of E, and free electrons are repelled. Right? The electromotive force, we call it, right, will cause the electrons and the holes to move. And so now, how can we define the velocity of the holes as well as the electrons? Essentially, what we call the drift velocity is equal to the magnitude of the electric field, or the electric field strength, times this constant here, which is called the hole mobility. For the n-type, or for the free electrons, I should say, the drift velocity is equal to the strength of the electric field times the electron mobility times a -1. And the reason why we have a -1 is because the direction in which the holes and the electrons will flow oppose one another. Right? One flows in the direction of the electric field, the other one flows in the direction opposing the electric field. And so it's not really so important. We're not going to go into depth about what drift velocity represents. We're going to use this as one intermediate step along the way to calculating current. So here are some constants we can use in those equations. Essentially, I mean, the strength of the electric field is going to be a variable. It's normally going to be provided to you, so you can insert that in. But we are concerned with the constants. So the values that we're going to use for silicon, the hole mobility is going to be 480 square centimeters per volt squared. And then for the free electrons, the mobility is going to be 1350. So what we see is that electrons move with a velocity 2.5 times higher than holes. That's going to have some implications later on down the road. Mainly, you get more bang for your buck with electrons. Meaning that if you're trying to increase conductivity, and you are going to use either a p-type or an n-type, a donor or an acceptor type of dopant, the n-type, the donor, will increase the conductivity faster, or that relationship will be greater because of this constant right here. This figure from the book simply just shows the relationship between the flow of holes, the flow of electrons. If an electric field with the polarity is shown here, plus minus, is applied to this just generic blue block of semiconductor material. So we are in Chapter 3. We're talking about semiconductors. Last time we talked about intrinsic semiconductors as well as doping of semiconductors. And what we saw was that an intrinsic semiconductor is not inherently very useful to us because the conductivity is relatively low. It's dictated primarily by temperature, which is not really a good, good situation for us in terms of designing electronics. And right, it doesn't allow us to build more complex structures like what we'll see today, the PN junction, field effect transistor, etc. So doping is definitely the route that we want to take. Now, next step, after we talk about the basic characteristics and the physics behind doping, we want to talk about current. We want to talk about voltage. Our goal, like I said last time, is to move away from a chemical or physical-based model towards an electrical model where, a lot like how we describe a capacitor or a resistor, it's a VI relationship. So in order to do that, we need to start discussing charge carrier movement. We need to start discussing current. Last time we talked about drift current. So drift current and drift current density, which is J, so that's equal to I over the cross-sectional area. So the current density is equal to conductivity times electric field strength, where conductivity is defined as this. Q, charge of an electron. P, concentration of the hole charge carriers. Mu P, mobility of holes. N, concentration of the free electron charge carriers. Mu N, the mobility of the charge carriers. And then the last two equations are just a definition of resistivity as opposed to conductivity. So this is talking about drift current. Today we're going to dive into another type of current which we have to consider, which is diffusion current. Can anybody explain to me what they think, just based on the name, what diffusion current might describe? So it's a different type of current. It's not dependent on an electric field or an electromotive force being applied. What do you think would make electrons move for a diffusion current? Say it again? Not exactly. So what is diffusion? Yeah. I'll go with you first.
When they spread out evenly to the ordinary.
Exactly. So the same thing applies here. Diffusion current is a current that's associated with the need for the charge carriers, whether they're electrons or holes, to create a more even distribution of them. But before we talk about that, let's do one more example. Example 3.3 asks us to find resistivity for two different cases of dope. Well, the first one's not doped, for semiconductors. Question A, find the resistivity of intrinsic silicon using the following values: mu n, mu p, and ni. So we have this equation for intrinsic, for resistivity. Which values do we have? Which ones are we missing? We know what the charge of an electron is. That's easy. We know what the hole and the electron mobilities are because they're given to us. What's P and what's N? Are P and N given to us, or do we have to use some sort of process to come up with them? Is Ni one of them? So what does Ni represent? Ni represents the concentration of free electrons for the intrinsic semiconductor. So we know that's going to be N, at least. What's P? For the intrinsic semiconductor, the charge carriers are created thermally. And they have equal numbers because every time we create an electron, a free electron, we also create an available hole. So for the intrinsic semiconductor, Pi is equal to Ni, which means that this is going to be both our P and our N. These are our mobilities, and we have everything we need in order to calculate what the resistivity is. So this is the number of free available holes, free electrons. We take our expression for resistivity, plug in Q, we plug in this here, this was given to us, plug in this here, this was given to us, and we end up with a resistivity value of 2.28 times 10 to the 5. So it's just a matter of understanding first what the question is asking you, because that's really the harder part. Plugging values into an equation, hopefully we all know how to do that. But understanding, okay, well there's one thing that's missing, right? I don't know what the P is, and realizing, okay, Ni is equal to Pi and using that. That's really a lot of what this chapter is all about. It's a mixture of, sort of easy math, applying some equations, and also having that deeper knowledge or that intuition to know when you have to use values in certain places. Okay, now look at the second one. So for the second part, it asks us to find the resistivity of a P-type doped silicon semiconductor with a concentration of acceptor atoms, 10 to the 16 per square centimeter. And using the following values, mobilities again are given and then Ni is given. Okay, so let's go back to the equation and let's figure out what we're going to do here. So again, they gave us mu n, they gave us mu p, that's fine. And then what they give us is the concentration of acceptor atoms and Ni. Do those do those satisfy or equate to either one of these values? Is Ni equal to N? No. Okay, which obviously, symbolically it seems like they would be the same. They're both N's, right? But we are talking about a p-type doped semiconductor, which means that this will be N sub p. N sub I is the concentration for the intrinsic semiconductor. They're very different. What about the p? What is this equal to? Did they give us a value for that? Does the concentration of the acceptor atoms play in here? Seeing people nodding yes. So what is that relationship? So N sub A, which is the concentration of acceptor atoms, is equal to the majority charge carrier, which is P sub P. So we know that this is going to be that 10 to the 16 number that they gave us. So we know this, we know this, we know this, we know this, and this one we have not come up with yet. So we'll see in a second. We've already learned how to come up with this, but we'll reiterate it. All right, so let's dive into this second half of the example. Okay, so like we said, the majority charge carrier concentration P sub P is equal to the concentration of the acceptor atoms, which is 10 to the 16. Makes sense. We have this equation down here. We're still missing our N sub P, our minority charge carrier concentration. How do we come up with that? We use this form here, which we have already seen. You're going to use this a lot. So by the end of this chapter, it'll become like second nature. You have normally the way these problems progress. You're given the majority. You're given the doping agent concentration. So you know the majority charge carrier concentration, and you use this equation to get the minority charge carrier concentrations. So anyway, we plug in Ni squared, which was given to us. We take this value, put it here, and what we end up with is 2.25 times 10 to the 4. And then now we have everything we need to plug into the resistivity equation. So we plug all those in, and we end up with 1.56 ohm centimeters. And this makes sense if you compare the two resistivity values, that the resistivity for the doped example, or the doped part of the problem, is significantly smaller than the resistivity for the undoped, because we expect, right, the doped semiconductor to be a lot more conductive. So those are the answers. Okay, now jumping into the other part of this, the diffusion current. So we already gave a little bit of an intro there. We essentially already stated this, which is that carrier diffusion is the flow of charge from areas of high concentration to low concentration in an effort or an attempt to even out the concentration gradient, right? And so diffusion current is this current associated with the diffusion, as the name would suggest. So if we take a look at an example, and this is from the textbook, let's imagine that we have a syringe that we can fill with these holes. Obviously, you can't really do this, not directly at least. And we take it and we inject it into the left-hand side of this block of silicon. What will happen is, at least initially, you'll have a concentration profile that will show up that looks like this. Where you injected it in, there'll be a lot. Thank you. There'll be a lot of holes, and then as you move further to the right, there'll be fewer and fewer. The x-axis here is the same as the x-axis here, meaning going further to the right. So what's going to happen is diffusion is going to occur. The holes will want to move to the right in order to even this out. And that's not due to any sort of electric field, right? It's just due to the diffusion force, which is the same diffusion force that you see when you drop, it's like the example from elementary school, right, or middle school, where you drop the red food coloring into the glass of water and it starts out all in the center, and then in a couple of minutes you have this pink glass of water because it's spread out. Okay, now how do we define this mathematically? Again, we're going to talk about diffusion current as opposed to diffusion current density as opposed to current. And so in order to get the actual current, you would need to multiply by the cross-sectional area, but that works always. Current density is equal to current divided by cross-sectional area. Okay, so let's move from right to left. First things first, as you would expect, the diffusion current density is proportional to the gradient. Okay, if the gradient, meaning dp dx is 0, if it's flat, there's not going to be any diffusion force. If there is a gradient, then we will have diffusion force. That is scaled by dp, which is what we call the diffusion constant of holes. Okay, it's given. And then times the charge of an electron, and then minus to account for the polarity of the holes, which are positive. We have a similar thing down here for the electron diffusion current density, which the slope of the gradient, the diffusion constant for the electrons, and then the charge. Now, the best way to demonstrate the use of this is an example. So we consider a bar of silicon in which a hole concentration P of X described below is established, and we could do this using that magical syringe method that we discussed a second ago. And so this is a mathematical description of what we saw. P of X will be equal to P sub 0 e to the negative x over LP. I'll talk about this in 1 second. But before I talk about that, P of O is the concentration at the left-hand side when x is equal to 0. One thing to note is that unlike drift current, diffusion current is going to be dependent on where you are in the block. Right? As you go further and further to the right, the diffusion gradient drops and eventually will flatten out. So the diffusion current changes depending on what slice you're looking at of the semiconductor. Now that plays into this value here, LP. LP is the diffusion length. I know that this chapter is just completely filled with all kinds of different new letter combinations that you have to memorize. So you might want to create your own little study sheet for just those values to get an idea. I mean, they will be on the cheat sheet, but be careful, and I'm going to send out a cheat sheet today, a copy of the cheat sheet. Not everything is going to be labeled. That's the caveat with the cheat sheet. You'll have all the equations. You won't have to memorize everything, but I'm not going to tell you exactly what's what. You will need to recognize what's going on. Okay, so diffusion length, what does that describe? That describes how far this particle is likely to diffuse. Now that will change a little bit randomly depending on the exact circumstances and probability. But how far will this particle diffuse before either it recombines or the diffusion force drops below the force required to make it move, meaning that the gradient has flattened out enough. So how far is it likely to diffuse? Okay. So now, in order to calculate the diffusion current density, we'll use this equation which was given to us previously. It says, right, J of x is equal to negative q dp dx. So the first thing let's do, let's take the derivative of this. P sub 0 e to the negative x over LP. So how do we take the derivative of this? Alpha e to the negative beta x. What's the derivative of that? Right? The derivative of that is negative alpha beta e to the negative x or beta x, right? So this piece we can pull out, and when we take the derivative, we're going to multiply by whatever the coefficient of the independent variable is, or the variable with respect to which we're taking the derivative. So what we end up with is, so this negative essentially cancels out this negative. It becomes positive. Q dp, and then now these are the two. This is the main coefficient, and this is the coefficient from the variable. So Q dp over LP, PO, and then e to the negative x over LP. So that's just taking a derivative, and then we plug in our value of 0. It asked us, what is the diffusion current all the way at the left-hand side when x is equal to 0? So we plug in a 0 here, which gets rid of that piece, leaves us with a 1, and so we're left with Q dp over LP, P sub 0. We have all those values. Those values were given to us in the problem definition. So we plug in our values, and we end up with 192 amps per centimeter squared. Now, if we want to determine what the current is from the current density, then we just multiply by the cross-sectional area, which they told us was 100 micrometers squared, and that gives us 192 microamps. So that's the diffusion current that we see associated with those conditions for that semiconductor. Okay. I think I mentioned this last time. I'm not sure if you remember. But there is a relationship between the diffusion constants and the mobilities, because they both describe, in one way or another, the likelihood or the resistance to making these particles move. Okay? Right? They both describe how hard it is for diffusion to make something move, or for an electric field to make something move. But in the end, the difficulty associated with moving them, they're both dependent on common parameters and characteristics. We're not going to get into all those details, but anyway, it makes sense that they would be proportional or related to one another. And so that's shown here. This is known as the Einstein relationship. And so what we see is that the ratio of dN over mu n will be equal to the ratio of dP over mu p, which is equal to something we call the thermal voltage. Now, this is not going to come up a lot in later parts of the chapter, nor particularly in the problems that much. But this VT does. So this thermal voltage we're going to use a lot, especially when we get to characterizing the VI relationship for the PN junction. At 300 Kelvin, it's going to be somewhere between 25.8 and 25.9 millivolts. One thing I will caution you about the book, they do this unusual thing where they keep flipping back and forth between 25.8 and 25.9. If I ask you to do a problem, I'll tell you which one to use. If you end up getting an answer to one of the homework problems and it's off by a very small amount, I recommend you go back and look at the beginning, and you probably use 25.8 and they use 25.9, or vice versa. That's a small thing that just comes up a lot. So, now to summarize a lot of what we have been talking about over the past class or so. These are all of the currents that we need to be concerned with. So first things first, there's two different types of currents. Again, drift current, which is excited or facilitated by an applied electric field. We have diffusion current, which is excited or facilitated by a gradient, a concentration gradient. Both of those currents, which can also be described as current densities, Again, you just multiply by cross-sectional area. R can be broken down into a component that's associated with the movement of electrons and the movement of holes, the movement of negative charge carriers, the movement of positive charge carriers. So you see we have two equations and both have two components. We've already spent a decent amount of time describing these equations and working with them in examples. And so we can see just one last pass through. Drift current density is equal to Q times the charge carrier concentrations times the mobilities times the electric field intensity. Diffusion current density, charge of an electron, diffusion current constant, diffusion constant, and then the gradient. Same thing over here. With, again, the main difference being that x doesn't show up anywhere in this equation. X does show up in this equation. This value is going to be constant between wherever the terminals of the voltage are that are being applied. This is going to be depending on what cross-sectional slice you're looking at. Okay, homework number 6.